Have you ever seen this before? Chances are you probably haven't. But in this video, we're going to talk about the crossover. A few months ago, I inherited this console, Sears console that's made by Silvertone, and it's got a um, turntable and AM/FM receiver amplifier in it, and two 12-inch woofers, mid-range, and a tweeter for each channel there. And I also inherited this combo 8-track cassette AM/FM phonograph as well. It's also made by Sears. I think my grandparents must have had a Sears credit card or something back in the 60s and 70s. But anyway, the console's like 1967, 66, somewhere in there. They went for around $400 back then, which was quite a bit of money. So I'm assuming it was got on credit. This I think is probably from the late 70s. It actually works. At least the phonograph part of it works. I haven't tried out the cassette or the 8-track, but it works. But that's not the topic of this video. The topic of this video today is crossovers and why do we need them, and why do you not all the time see them? And they're kind of a unseen part of a stereo system these days. So let's talk about that. Okay, first of all, what is a crossover? Crossover is a circuit that basically takes and picks apart all the different frequencies that are in an audio signal and directs them in the right path, so that your high frequencies go to a speaker that's better suited for high frequency, has a better high frequency response, and your mid-range frequencies go to a speaker that's better suited for mid-range frequencies, and your low frequencies go to a speaker that's better for low frequencies. We typically refer to these as a tweeter for the high frequencies, mid-range speaker for the mid-range frequencies, and a woofer or subwoofer for your low frequency signals. So why do we want this? Well, unless you have a speaker that's what's called a full range speaker, many speakers aren't designed to carry the full range of human hearing, which is approximately 20 hertz to 20,000 hertz. Unless you're old like me, and then you can't hear much above 12,000 hertz. But if you put all of these frequencies into a single speaker, that speaker is having to reproduce all of those. So it's got to have a wide frequency range or frequency response in order to duplicate those. And you're basically, what you're doing is you're kind of compromising, because you're not getting the full effect of the high frequencies, you're not getting the full effect of the low frequencies, and you're probably getting a good mid range, but it's a compromise with a full range speaker. Most of your guitar amplifiers, things like that, will have a single driver, single speaker, and it's typically a full range speaker. In most hi-fi systems, stereo systems, you're going to have either a two-way or a three-way style of speaker cabinet, and it's going to consist of, the three different drivers like you see in this picture here. So we have to have some way of getting those frequencies to those particular speakers in the frequency range that those speakers are like to operate in, so that we get the benefit of all of those. So let's look at that. What does that look like? So here's a schematic of how a typical crossover might work for a three-way crossover, which would be, a tweeter, a squawker for your mid-range, and your woofer, which will handle your low frequencies. Essentially what you're doing is you're creating three different types of filters here. You're creating a high pass filter for the tweeter, band pass filter for the mid-range speaker, and a low pass filter for your woofer. And this is one of the more elaborate types of crossovers that you'll see out there. And it's got a lot of extra components in there that you may not find in your normal crossover arrangement in your speaker cabinet. And I just wanted to point out here that a lot of times you have a speaker cabinet that's got these three speakers in there, and you refer to that speaker cabinet as a speaker. And typically what we refer to as each of these three different devices in here as drivers. So, you have a three-way speaker, for instance, with three separate drivers in it. And each one of those is considered a driver. But I guess separately, if that's all you had, they would be speakers as well. But that's just kind of the terminology that's used. But you can find much more simpler types of crossovers. We'll take a look at another one here, and we'll kind of break it down from there. Okay, so here we have a diagram showing the circuitry needed to form a very simple type of crossover. It's probably a little more understanding than that previous diagram that we had. And let me just start out by saying this. A lot of times you don't see this circuitry because it's incorporated into the speaker box itself, and it's in a sealed container, and it's behind the baffle, in an enclosure or something like that. Or in the case of like car audio speakers, where you have like a three-way speaker, all of this stuff is somewhere, usually in a little box or something like that. And then the leads go to each individual driver, is what we refer to them as. Your tweeter, your mid-range, and your woofer. Where you may see one of these crossover circuits outside of a speaker package is when people are, wiring up like subwoofers for extremely low frequencies in their car audio and stuff like that. They may break out a crossover circuit to handle the very extreme low frequencies for that subwoofer. It takes a lot of energy to push the low frequency sound waves, so you have to have a larger speaker, move more air, and that's why it's just efficient to break out these frequencies to the individual driver types that are capable of handling these types of frequencies. So your tweeters are generally smaller in size, mid-range obviously a little bit larger, and then the woofer and subwoofers are larger than that. But as we can see over here, if you can follow my mouse, we have on the top, we'll go with the tweeter first. Basically, we form a high pass filter here, with our load being the inductor coil of the speaker itself, okay, and a capacitor right here. And you can think of a capacitor, and I'll probably make another video with all the math on this to figure out what the frequency cutoff is for this type of circuit, and how to determine what the frequency cutoff is going to be, and what these sizes are going to be. But for now, we're just going to look at basically how this works. So essentially you have a capacitor in series with your load, and then you have an inductor in parallel with your load. So basically you have two inductances in parallel, and they add in parallel just like two resistors would add in parallel. So this is going to be a lower value than the lowest inductive value here. But again, we'll get into the math on that in another video. I don't want to bog this video down with that. I'm just want you to kind of understand how this is happening. But you're basically forming what's called a high pass filter here. So anytime you see a capacitor and a resistor, or a capacitor and an inductor to ground, we'll say that this positive side, although there really isn't a positive side per se in AC, But if we just keep with the polarity marks here on the speaker, so that they're all driving at the same time, forward and backward, we'll say this is the positive side, and we'll say this is the negative side, and it's most often grounded. So we'll call this the ground. Anytime you have a capacitor with a resistor or an inductor to ground, as you can see here, it's tied back to this point, then you have what's called a high pass filter. And I always remember this because if the capacitor is high, then it's a high pass. If the capacitor is low, in other words, going to ground, then it's a low pass. And we'll look at that here in a minute when we talk about the whoopers. But basically, you can look at a capacitor. It's an inverse function, meaning the frequency cutoff is over 1 or 1 over a value. And depending on what you're using, inductors or resistors, is a different formula. But it's basically an inverse function. So the higher the frequency, the less impedance this capacitor imposes on that current. The closer that current frequency gets to 0 or DC voltage, the more impedance this imposes. As a matter of fact, if it was DC, it would block it altogether. So your high frequencies are going to pass freely through this capacitor, okay? And then your low frequencies, lower than the value that you've sized both of these to for the frequency cutoff, is going to be shunted to ground. And it's gonna have a low resistance path to ground, lower than the resistance of the speaker. So basically, only what frequencies you want to attenuate here, extenuate, I should say. That's what's going to go through the speaker. Okay, that's what's going to drive the speaker. So that's the high pass filter part of it. When we get here to the mid range, we set up what's called a band pass filter, and that is a capacitor. And in this particular version, there are many other ways to make all of these, but in this particular version, we've got an LC filter network here, just like we had up here. But in this case, the capacitor and inductor are in series with the load. And basically what you're doing is you're sizing the capacitor for the high frequency that you want to pass through easily, and the inductor for the low frequency that you want to pass through. So you're basically creating a curve. And again, we'll look at the Bode plots and the frequency response curves and the math behind all this in a later video. I'll break it out, but maybe it'll be a part 2 or just a separate video altogether. But basically, this is going to create a band of frequencies somewhere in here, maybe 8,000 to 2,000 or something like that. Whatever values you choose for this is going to determine that frequency range. And those frequencies will pass through here and go through the speaker. When we get down here to the low pass filter, again, the capacitor now is low instead of over here it was high. The capacitor now here is tied to ground. And what this does is it makes all of your higher frequencies shunt straight to ground based off of the relationship between these and the values between these two components right here. And all of your low frequencies will have, no problem going through your speaker here. And that's what will be used in the process for your speaker. So you'll get all your low frequencies out of this speaker right here. So you can think of a capacitor as blocking low frequencies, basically, right? And passing higher frequencies. Again, it's the inverse. So it's an inverse function. It's got a higher impedance to low frequencies, and it's got a lower impedance to higher frequencies. An inductor is exactly the opposite. It's got a direct relationship on the formula and all that. And you'll see that when I break out the math, but I don't want to really get into that right now. So as you can see right here with 3 speakers, and each one of them is basically taking on the frequencies that they're designed for, then you get, really good highs, you get really good mid-range, and you get really good low frequency responses out of all three of these drivers. And in doing so, you kind of maximize the sound quality. However, there are drawbacks to a crossover network. All of these components, all these reactive components, uh, shape the tone somewhat. It also There are also loads on the amplifier, and also you can also have some phase shifting go on where the sine wave coming out of this tweeter doesn't necessarily track with the mid-range sine wave or the low woofer sine wave. So you have some phase shifting going on here, and there's some more sophisticated types of crossover circuits that kind of compensate for that and keep that from happening as bad. But with most of your, commercial low end gear, this is probably how it's going to be. Maybe a little more complicated than this, but the one out there in my cabinet that we saw earlier in the video is set up pretty much like this. So that's how it is. Well, I hope you got something out of this. And like I said, I'll be breaking this out a little more in detail in another video. We'll be going over the math, how to determine the cutoff frequencies using a capacitor and a resistor, capacitor and inductor resistor, all the different types of filter networks that we can come up with, and how you can create your own low pass, high pass, and band pass filters for a crossover network. Until then, thank you for watching and have a good day.